start with state transition matrix using Cayley-Hamilton theorem. In previous classes, we have seen the various methods for calculations of state transition matrix. We have seen a power series method, then we have seen Laplace transform method, and also we have seen a diagonalization method. Today we have to see another method which can helps us for state transition matrix. That means we can get a state transition matrix by also another method. That method name is called Cayley-Hamilton theorem. This theorem is very important. It can be useful in various applications, particularly if you want to calculate the inverse. For that also this particular method can be useful. Now we will see what is that theorem. This theorem states that every square matrix satisfies its own characteristic equation. That is, if you take any matrix, if you determine its characteristic equation, it will satisfy it. That is a very important theorem. How it is possible? That is, it says if you take a matrix, if you take this as a matrix A, and let us say it is 0 1 minus 2 minus 3, and now we will take its characteristic equation, that is lambda I minus A equal to lambda I minus A, that is equal to, so here lambda 0 0 lambda minus A, here is 0 1 minus 2 minus 3, and if you solve it, you will get lambda minus 1 2 lambda plus 3, and if you take its determinant lambda I minus A equal to lambda square plus 3 lambda plus 2 equal to 0. Now this is the characteristic equation in terms of lambda. Normally we are calculating the eigenvalues of this matrix, and if you replace this eigenvalue, it becomes 0. But Cayley-Hamilton theorem says that here instead of this lambda, if you replace A is the original matrix. If you replace A in terms of lambda, you will get A square plus 3A plus 2I, and that is also equal to 0. That is lambda and A we can interchange. This is the basic theory of the Cayley-Hamilton theorem. Now its applications. The first application is inverse of matrix, and second one is the state transition matrix. Or your topic is state transition matrix, but in here we will also determine the inverse, and we have seen that the applications of inverse means the determination of inverse is helpful in various approaches. It is useful in case of the Laplace transform approach. It is also useful in various say in case of getting the state space model from the given transfer functions, that is, or that is this particular this particular inverse is helpful, in getting the transfer function model from a given state space model. We have seen this part earlier. So it has wide applications, and however here basic purpose is to getting a state transition matrix. Now first of all we will see how to calculate the inverse of the matrix using Cayley-Hamilton theorem. Now we start with the concepts. So our main input is A matrix. So input is A matrix, and let us say it is n cross n matrix. Now we have to take lambda I minus a, that is the characteristic equations, and we will take the determinant of it, that is equal to lambda raised to n a of n minus 1 lambda n minus 1 plus a of n minus 2 lambda n minus 2 plus a1 lambda plus a naught equal to 0. Now this is the your characteristic polynomial in terms of lambda. When we are working on S domain, we can write down S instead of lambda, that is S raised to n a of n minus 1 S raised to n minus 1 up to a0. Now our aim is to get the inverse. So now this is the characteristic equations. So what we can do if we further, we will apply the concept of the Cayley-Hamilton theorem. As we have seen the concept of Cayley-Hamilton theorem, that is lambda can be interchanged with a. Therefore here we will convert this lambda into a. So according to Cayley-Hamilton theorem, we can write down the above equation as a raised to n a of n minus 1 a raised to n minus 1 a n minus 2 a raised to n minus 2, this process repeated, then here a1 into a equals to 0. So now this equation we have written. Now our main purpose is to get the A inverse, that is our base purpose is to determine A inverse. Now what we can do, to this equation we pre-multiply A inverse both sides. So if we multiply A inverse to these particular equations, what we will get? So this n, when we multiply by A inverse, it becomes a n minus 1 plus a n minus 1 a, it becomes n minus 2 plus a n minus 2 a n minus 3, and this process repeated, it becomes a1, I can say I plus a0 into A inverse equal to 0. Now our purpose is to get A inverse, so A inverse we already got. So what we can do, all these terms, this a of n minus 1 to a1i, we move on the right side, and this a0 a inverse we keep it on one side. So what we will get? So this A inverse equal to this, and as this shifting to right side, so what we will get? We will get a of n minus 1 a n minus 1 a n minus 2 plus a n minus 2 a n minus 3, and here this process repeated a1 into I, and this is basically your A inverse. We have seen various methods for getting A inverse. If you want to A inverse, there are various methods. One, A equals to adjoint of A divided by a determinant of A. This is one, and now this is the alternative approach. We have also seen a Leverage algorithm to calculate the inverse, where this is based on the trace of the matrix. That means we have seen the Leverage algorithm is A, suppose here A11, A12, A21, A22. So this trace equal to A11 plus A22. So based on this trace, we have also determined the inverse. Now this is an alternative approach to get inverse. Now we will see which method is found to be simple. We have seen that if you this particular approach, a Leverage algorithm for determination of inverse, as the order increases, this is better. But for lower order, we have seen that this adjoining of a determinant is helpful. Now we will try to solve an example to calculate the A inverse of a given system matrix. Suppose we have taken a matrix A equal to 0 1 minus 2 minus 3. This is A matrix. Now we have to take lambda minus a. If you take lambda minus a, it becomes lambda minus 1 to lambda plus 3. Now we want characteristic equations. So characteristic equation becomes determinant of lambda minus a. If you solve it, we will get lambda square plus 3 lambda plus 2 equal to 0. But our aim is to A inverse, but we have got equation in terms of lambda. But we have a Cayley-Hamilton theorem which states that every square matrix satisfies its own characteristic equation. Now we can convert this lambda by A. So if you convert this lambda by A, so according to Cayley-Hamilton theorem, this above equation can be written as, that is according to Cayley-Hamilton theorem, above equation can be written as a square plus 3a equal to 0. Now a square 3a plus 2 we have got, but we want A inverse. So best option is we apply or we multiply A inverse to both sides. If you, this is equation, if you multiply it by A inverse, this becomes A, this becomes 3i 2 A inverse equals 0. That means this A order of 2 changes to 1, this A and A inverse neutralize, so become identity matrix plus 2 into A inverse. Now we have to solve these equations. So we can write down as 2A inverse minus A plus 3 into I. Now what is A matrix? A matrix is 0, 1, minus 2, minus 3, plus 3, identity matrix is 1, 0, 0, 1, and total this multiplied by 1 by 2. Now this particular matrix we have to solve, then divide by 1 by 2, and after solving this we will get the A inverse as minus 3 by 2 minus 1 by 2 1 0. Here is a simple mathematics, just you multiply 3, then additions, then 1 by 2, we can come across this A inverse matrix. So we will find that in a very simple manner we have got the A inverse. I think particularly for second order system, I think this method is better than this Leverage algorithm as well as our conventional adjoining and determinant approach. But again here the problem is that if you increase the order, for example here we have a raised to 4, or we have this particular matrix, this matrix is say 4 cross 4, that means finally this equation will get in terms of a cube, a square. That means here we have to multiply this A matrices. So it may increase your computations like this. But as far as we will find as for some lower order, this Cayley-Hamilton theorem is quite useful. Now we go for the second concept, state transition matrix. Okay, now we go with the concept of state transition matrix. State transition matrix means e raised to at, that is e raised to at. And as I discussed earlier, we have seen the various methods to get the e raised to at, and we will find that this Cayley-Hamilton theorem is useful to getting the state transition matrix. Just looking after a problem, just it satisfies any square matrix satisfies characteristic equation. It is hardly believable that how can this particular concept is useful for state transition matrix. Now we will see some logic behind it. The logic says that suppose if we had taken one particular functions, say we have taken a function f, and let us say it is a very higher order, it is very higher order, To this f, if you divide by delta, definitely the degree of this del is lesser than f, f is very higher degree. So, f is divided by delta. So, what we will get? We will get one quotient and also we will get the remainder. So, here when this f divided by delta will get q plus remainder r divided by del, and that means these above equations f by del equal to delt q delt plus r, and if you equate this, what we get equation f q delt plus r. Assume that delta is the characteristic polynomial of any matrix. This delta is the characteristic polynomial of a matrix, that is, if you having, we take say this A matrix, A is a matrix, and this delta equal to lambda I minus A. So, definitely if you take determinant of this, it become lambda minus A. So, this determinant is 0, this determinant lambda I minus A equals 0. So, this means this, if this delta is 0, if you replace here, what will get? F equals to r. Now, this f equals to r and r is the remainder, and definitely degree of this r is also lesser than this delta. So, we get f equals to r. Now, this is the basically the concept that is f equals to r. Now, this concept we have to use in getting the state transition matrix. Now, how will you do it? Now, we take a polynomial which is represented in terms of lambda, and let us say it is f of lambda. F of lambda is the polynomial. Then consider a square matrix A, consider a square matrix A, and now it can be written as del of lambda equal to lambda I minus A, and this is f of lambda, and as I told you that f of lambda is higher degree than del of lambda. Now, we divide this. So, if you divide this, f of lambda divided by del of lambda equal to, this is equal to q of lambda plus r of lambda divided by del of lambda, and after solving it, it becomes f of lambda equal to q of lambda to del of lambda plus r of lambda. Now, we assume that this del of lambda equal to 0, and therefore, what we can say, this f of lambda equal to r of lambda. But now, here is coming the concept of Cayley-Hamilton theorem. This lambda can be interchanged with A matrix. So, therefore, this f of A is equal to r of A, and this r of A can be written as, this r of A we can write down as alpha 0 plus alpha 1 A plus alpha 2 A square plus this process repeated till alpha n minus A raised to n minus 1. That means, degree of this r of A is lesser than this both del of lambda, f of lambda, or del of A and f of A. And now, this is the r of lambda. Now, here this is f of A equals to r of A, or we can say this f of lambda equal to r of lambda. Now, we want to determine the state transition matrix. Now, state transition matrix is nothing but E equal to AT, or this is equal to say lambda t. So, here depend upon the eigenvalues. Suppose if you are in a system, we have two eigenvalues lambda 1 and lambda 2. So, this for one lambda 1, this E of lambda 1 t equal to alpha 0 plus alpha 1 into a, alpha 1 into say let us say in terms of lambda. And for another lambda 2, e raised to lambda 2 to t equals to alpha 0 plus alpha 1 into lambda 2. That means, whatever be the eigenvalues for a given system matrix, suppose there are two eigenvalues, then here this n equals 2 minus 1, that is alpha 1 into a, that means our equation equals to, we have to take alpha 0 into a. So, as the number of eigenvalues we are increasing or the order of the matrix increases, this term will increases. Therefore, we have to take r of lambda, r of a or r of lambda equals to alpha n minus 1 a raised to n minus 1. So, here e raised to lambda 1 t, e raised to lambda 2 t, and now you have to solve these equations to get the alpha 0, alpha 1, and if you calculate it, finally we will get the equation of f of a as e equals to e raised to a t. So, this is the concept which I told. At basic concept, as I told that it is f of a equals to r of a, f of lambda equals to r of lambda, and then we have to calculate the eigenvalues, and for each eigenvalues we have to assume functions, and that is written in terms of alpha 0, alpha 1 for first, second, like this, and we have to solve these equations to get the values of alpha 0 and alpha 1. Now, we solve example and again you see in detail how to get the state transition matrix. So, your question is find e raised to a t, that is equal to f of a for a given matrix A equal to 0 1 minus 2 minus 3. This is the problem. Now, we have to use a Cayley-Hamilton theorem. Now, the first step is we have to determine its characteristic equation. So, characteristic equation for this matrix A, that is say lambda I minus A, that is equal to lambda minus 1 to lambda plus 3, and this is equal to lambda square plus 3 lambda plus 2 equals to 0. So, lambda square plus 3 lambda plus 2 equal to 0. Now, we calculate the eigenvalues of this. So, eigenvalues for this will get as lambda 1 equal to minus 1, lambda 2 equal to minus 2. These are two eigenvalues. Now, these two eigenvalues we have determined, and our purpose is to get e raised to a t. Now, we will take first function, that is a f of lambda 1 equal to e raised to lambda 1 t, that is equal to alpha 0 plus alpha 1 into lambda. That is f of lambda 1 equal to e raised to lambda 1 t equal to alpha 0 plus alpha 1 into lambda 1, because e and a and lambda can be replaced, can be interchanged, that is lambda 1 and a can be interchanged. Therefore, here e equals to lambda 1 t, alpha 0 plus alpha 1 into lambda 1, and you know why we have not taken alpha 2, because here this is because here a raised to n minus 1, that is n is 2, therefore, we have taken this equation till alpha 0 plus alpha 1 into lambda 1. Now, the first is replace, say lambda 1 equal to minus 1 in above equations. So, what will get e raised to minus t equal to alpha 0 minus this alpha 1 is minus 1. So, it becomes alpha 0 plus alpha 1. This is the first equation we got. E raised to minus t equals to alpha 0 minus alpha 1. Now, coming to the another equations, that is lambda 2 equals to minus 2. Now we replace lambda 2 equals to minus 2 here, that means here function of lambda 2 e equal to lambda 2 into t plus alpha 0 plus alpha 1 into lambda 2. Now here if you solve it, that is replacing lambda 2 by minus 2 gets minus 2t alpha 0 minus 2 alpha 1. Now this is equation number 2, this is f of lambda 2. Now this equation, this and this, and now we can solve these two equations and we can get the unknown values of alpha 0 and alpha 1. That is, there are two equations, two unknowns, so we can easily get the values of alpha 0 and alpha 1. So after solving these two equations, we will get the values of alpha 0 and alpha 1. So this alpha 0 after solving we will get as 2 into e raised to minus t minus e raised to minus 2t, this is alpha 0, and this alpha 1 equal to minus t minus e raised to minus 2t. So now we have got alpha 0 and alpha 1. Our basic purpose is to get the f of a, and that is equals to e raised to at. Now this e raised to at equal to f of a, that is equal to alpha 0 I into alpha 1 into a. This is basic equations. And why this is obtained? Because of the Cayley-Hamilton theorem, because a and lambda can be interchanged, because you see all these results, all this calculation we have done in terms of lambda, we have got alpha 0 and alpha 1, but to get e raised to at we have changed this alpha by a, that is e raised to at equal to f of a alpha 0 I plus alpha 1 into a. Now we replace the value of alpha 0, alpha 1 and a is the matrix, this matrix, A is this matrix A. Here in this equation you just see what we will get. So here this alpha 0 into I is the identity matrix, and we have already got alpha 0 as 2 e raised to minus at e raised to minus 2t. So here we can write down this as 2 e raised to minus t minus e raised to minus 2t, this is 0, 0, again here 2 e raised to minus t minus e raised to minus 2t, like this, plus alpha 1 into I. Now here alpha 1 we have already determined this one, and this is multiplied by a. So when this alpha 1 is multiplied by a, so we will get equation as, or results as 0 e raised to minus t minus e raised to minus 2t minus 2 e raised to minus t plus 2 e raised to minus 2t. Here we will get minus 3 e raised to minus t plus 3 e raised to minus 2t. So here this alpha 0 I is the thing with this part, and this alpha 1 a equals to this, and now we add this, all these elements individually. So we will get the result as 2 e raised to minus t minus e raised to minus 2t. Here we will get e raised to minus t minus e raised to minus 2t, and here we will get as minus 2 e raised to minus t plus 2 e raised to minus 2t. Here we get e raised to minus t plus 2 e raised to minus 2t, and now this is e raised to at. So we will find that in this way we have determined the straight transition matrix. Transition means transition forms of state from initial time to final time. These results we have got by means of Cayley-Hamilton theorem. But now here we have taken a case where their eigenvalues are distinct, that is lambda 1 equals to -1, lambda 2 equals to -2, and if we have easily we have got the result, that is replacing lambda 1 equals to -1, then we have replaced lambda 2 equals to -2, and somehow we got results. But now here is a problem. Suppose if say lambda 1 and lambda 2 both are same, assume that the case is that lambda 1 equal to say -1, and again say lambda 2 is also equals to -1, or say repeated eigenvalues, then how to manage this equation? Because if you take lambda 2 -2, we come across a similar type of equations, and they are difficult to solve. Therefore, we have to use certain logic in order to solve this type of example. Now we are going to solve example assuming that there are repeated eigenvalues of a given matrix. Now we will take example, say A matrix is equal to 0 1 -1 -2. This is given matrix A, and purpose is we want to determine e raised to at. This is the aim. Now what is the first step? We have to determine lambda I minus a. So the function f of lambda equal to lambda I minus a, that is equal to lambda minus 1 1 lambda plus 2, like this. Now we solve these equations. So after solving we will get lambda square plus 2 lambda plus 1 equal to 0, and if you solve this equation or we calculate the roots of this equation, so what we will get? We will get lambda 1 equals to -1, and again same lambda 1, lambda 2 equals to -1, same eigenvalues, lambda 1 -1, lambda 2 equals to -1, they are repeated eigenvalues, and our purpose is to get the state transition matrix. Now how will we proceed further? So first of all we proceed with the initial step, that is f of lambda equal to alpha 0 plus alpha 1 into lambda, that is equal to r of lambda. Now here function f of lambda, that is -1, that is equal to e raised to lambda t, again alpha 0 plus alpha 1 into lambda. Because they are repeated, we have taken a generalized term lambda only. So here we replace lambda equal to -1, so we can write down as minus t e raised to minus t equal to alpha 0 minus alpha 1. Now this is the first equation we have got. So e raised to minus t we have got. Now the problem is, if you replace here another lambda by -1, so if you replace another lambda, lambda equals to -1, as because this is another lambda, we came across same equation, this. But problem is that if both equations are same, how do you determine the alpha 0 and alpha 1? Then which procedure we applied? So in that case we have to use the concept of the differentiations. So what we can do here, we differentiate this equation dd differentiation with respect to lambda of function of f of lambda, say at lambda equals to -1, equal to differentiation of lambda equals to r of lambda at lambda equals to -1. Now r of lambda is this one, alpha 0 alpha 1 lambda, f of lambda we have written like this. Now this d of d lambda, what is f of lambda? F of lambda equal to e to lambda t, and here differentiation of lambda, that is equals to alpha 0 plus alpha 1 into lambda. Now, if you differentiate these equations, so we will get this equals to t e raised to lambda t, and here we will get, if you differentiate this alpha 0 becomes 0, and here in terms of lambda we get alpha 1. And now, if you replace here this lambda equals to minus 1, so we will get alpha 1 equal to t e raised to lambda t. And now, about alpha 0, this alpha 0 equals to alpha 1 plus e raised to minus t, and now here alpha 1 is t, and now lambda is, that is this t e raised to minus t. So, here t e raised to minus t plus e raised to minus t. So, we take e raised to minus e t common, we will get t plus 1. Now, here alpha 0, and what is alpha 1? Alpha 1 is this part, this complete part, alpha 1, and this complete part equals to alpha 0. That means, here we can finally write down this as alpha 0 equal to e raised to minus t plus 1, and here this alpha 1 equal to t e raised to minus t. These are two, alpha 0 and alpha 1 we have determined. So, you will find that even though they are repeated, by differentiating this equation we have come across this particular result, alpha 0 and alpha 1, and now the rest of the procedure is very simple. That means, here f of a equal to alpha 0 into I plus alpha 1 into a. Now, if you replace the values of alpha 0 as e raised to minus t, t plus 1, 0, 0, e raised to minus t, t plus 1, this is this particular portion, this part, and now alpha 1 into a. So, if you multiply this alpha 1, this one t e raised to a t to this particular matrix A, what we will get? So, we will get result as 0 t e raised to minus t minus t e raised to minus t minus 2 t e raised to minus t. Oh no, this is nothing but the result of this portion, and now if you have to add this, so after adding this we will get the state transition matrix as e raised to minus e t, t plus 1. See here, this part plus this we will get as t e raised to minus t, and the 0 plus minus t e raised to minus t we can write down as minus t e raised to minus t, and now this portion t plus 1 minus 2 t e raised to minus t. So, after adding this we will get e raised to minus t minus t e raised to minus t, and now this is f of a, or you can see e raised to a t as the result. Now, this is the state transition matrix of a given system when there are, say, repeated eigenvalues. So, in this way we have completed the part concerned with the state transition matrix. We have seen 4 methods. First of all, we have seen a power series method, then we have seen a Laplace transform method, then we have seen the concept of diagonalization to getting the state transition matrix, and this last one is the Cayley-Hamilton theorem method. So, based on the problem we can use any of the method, but you will find that using all these methods we will come across the same result, and this concept is also used in the case of the getting the state equation. We have seen the state equation also, that is x of t equal to e raised to a t into x naught for unforced system, that is the state equation is also depends on this state transition matrix. Now, these are some references. Thank you.